Thanks for tuning in to Stay Sharp with Razorleaf, your secret weapon for all things digital in products and manufacturing. What do we mean when we say character of the data? In this episode, Jen Farello and Jonathan Scott answer this question and delve into the complexities of data in digital manufacturing. They explore the nature of data, the importance of understanding its character, and the challenges of integrating various data systems. They cover key concepts such as digital thread, digital twins, and the differences between taxonomy and ontology in data representation. Using real-world examples, they highlight the significance of managing data effectively to ensure successful product development and manufacturing processes. Let's listen in.
Welcome back, everyone, to Stay Sharp, the podcast about all things digital-related products and manufacturing. I am Jen Farello, and I'm joined today by my colleague, Jonathan Scott.
Hi, everybody.
And when you spend time talking about all things digital, the topic of data is bound to come up, whether it's data creation, data management, quality of the data, integration and the flow from one application or functional silo to another, IoT, AI, data always comes up. So with all of that data, it begs the question, is it all created equal? Can it all be handled the same, managed the same? After all, it's just data, right? It's just bytes. Maybe not. But that's
just data.
That's what we're here to discover today. So today we wanted to dig in a little bit and talk about the character of data and product data and connect some of the academic terms that you hear out in the industry and industry buzzwords with the real issues that people are facing as they build out digital threads and start to develop product digital twins.
I think also explore just, that point you brought up about data. Is data simply the collection of bytes and strings and integers and all those things? Or is there more to it that we need to pay attention to? Because, it's data. It's not that exciting. So we need to dig into it a little.
Should I give everybody a hint? It's not all the same. Okay. Anyway, well, sorry.
Foreshadowing.
I think most people agree today that a digital thread or digital twin is built with the data that resides not just in one system. One system would be nice, but that's not reality. Would you agree?
Yeah. It's, it was easy to think of that when this topic first came up, like, oh, I want to build a digital thread. I just need to put more things in my PLM system or PDM or grow it out or expand it, that kind of thing. But I think quickly people came to the conclusion that, well, we already have other business systems that we need that have product data in them that mean, well, to really have a good digital thread or to build out a digital twin for a specific purpose in our business, we need that other data. And it's not that we need to go grab it from there and pull it into PLM, but we need to keep doing what we do over there. And the over there, by the way, might be 2, 3, 4, 5, 10 systems. But we have to keep doing those things, and we have to do what we do in PLM. So we might be growing that data set for a better digital thread in all those places, but we're not going to centralize it all. So to your point, I think everybody's on that page today, I think.
But it's easy, right? Because data is just, it. Once you got it, you got it. Doesn't change.
That's right. It's simple. Once you're managing it.
Yeah, but it also doesn't change, right?
Right,
data
right.
is, nothing changes as you're developing a product or manufacturing anything along those lines.
That's a great point.
Maybe it's a little dynamic.
Yeah. So the problem of how do you connect it would be simple if it didn't change. But, when you think about using it in a digital thread or a digital twin to that point, you have to decide sort of what snapshot you want to use. Because, let's just be practical about it. A product is developed. Developed means that it changes, right? It doesn't it doesn't just spring out of someone's head like, oh, well, that is the cell phone we meant to make. Done.
That'd be nice.
It wouldn't it? But, we seem to have a new version every year. It's amazing how that happens. And that means that the thing is revised and it's changed over time. So when you decide, oh, I want a digital twin of that particular product that I'm launching, you need to decide what point in time is that. And is it when you were trying out this new feature capability, or it's the one that you decided not to finish out, which one are you modeling to check? Or, if you're representing the one that somebody has in their hand, digital twins that model physical things out in the real world, how do you get exactly the configuration that they have from the model year thing that they purchased? All of that means that the time-based piece of this is critical. And to your point, it's dynamic. All this data and all these systems just marches on over time. So integrating it is tricky. It's not, oh, hey, there it is. That's what it looks like. Now let's just tie it up.
Oh, we're all engineers. We love a good challenge. So,
Don't we?
so the data is dynamic. It's always changing, and it's all in all of these different systems. But surely all of those systems manage the data in the same way, right?
Of course.
Sweet.
There's I think there's this universal translator. It's like the Rosetta Stone or something.
Now, my history, my entire career has been spent in 3D data translation, so I know that's not the case.
Exactly. So that is maybe one of the biggest problems here is that every software vendor who writes a tool that's meant to deal with some kind of product data has their own representation of it. Now, lots of them will support standards, and there are lots of standards out there. That's another part of the problem. But there are plenty of standards out there to say, hey, let's all have the same representation of the data. But frankly, this is the push and pull of software development and tool development is everybody's got a little better idea. Well, hey, if we represent it like that, then you could get this insight into your product, and that would be a benefit for you, Mr. Customer. So therefore, it's a benefit for me, Mr. Software Vendor, to offer you that capability. So now my data model or representation of your product is different from my competitors on purpose, right? So it's a good thing and it's a bad thing all at the same time. But it gets to that reality that you just said of nobody has the same exact view of how to represent product data. If you're lucky, maybe they have multiple views or flexible views that let you sort of take, hey, vendor A could represent their data in these 10 ways. Vendor B could do it in these 8 ways. Oh, they have 2 that overlap. Let me pick the one that works best for me, and it helps you, marry it together better. That's if you're lucky.
Yeah, my career would have been really short in data translation if that were the case. So I know
most people aren't lucky, right? On that point.
Not on that point. So it sounds like actually, and I know this to be the case because like I said, it does happen in 3D data translation as well, getting one format to another. So successfully integrating the systems, getting them to work together requires not only understanding the underlying data itself, but also understanding how those systems represent that data in their data models, right? So it's understanding a lot of different moving pieces.
That's right. And there are other moving parts too that maybe we shouldn't get into today. I think it makes sense for us to pull in another colleague to talk about this at some point. But even if you understand how those systems represent the data and you could somehow rationalize their models of the data, then you've still got the challenge of the underlying technology they use to create those data models, right? Oh, I use this language, I use this database, I use it, so there's lots of tech under the hood too. That's another thing to deal with, but a problem for another day. But that's another piece of this when you peel back the layers of this onion. But yeah, I think that issue of how do you get those data models? How do you rationalize them? Where do you do that? That's all a pretty big question.
So, easiest way, we're all engineers. So easiest way, can you give me an example? Paint me a picture.
Yeah. So I think an example of where these data models can be an issue, and it's not even just the data models of the systems, but it's the conceptualization that the people have who write the integrations that can be part of the issue, right? So let's talk through an example. For those folks listening who are familiar with product lines, product families, variant management, that kind of concept in PLM systems, you may be aware of this already, but I'll try and describe it for those who maybe aren't aware of this. When you're modeling a product line in a PLM system today, and even in other business systems, a common way of doing it is to create bills of material that are overloaded. So you'll take the bill of material for like the first product in the product line, and you'll model that out, right? Parents and children. Let's assume it's something really simple. When you add in that second product from the product line, it's going to have a couple of different features, which means it'll have a couple of parts that are different than the first product. Well, with an overloaded bill of material, what you're doing is those new parts, you're adding them in there also. And for the third product and the fourth product, you're adding all those in there. So what you end up with is this bill of material that represents the superset of all possible children of that product, of all the products in that product line, in that family, right? And then the idea is you've got that overloaded bill of material that then you filter out, right? So you filter it back down to product 3 or product 5 or whichever it is by applying filters. And this is where different systems come into the play, right? They can filter by country you're selling it in, or is it the blue one or the red one or the high voltage one or whatever it is, right? But the idea is you'll have this overloaded bill that then you filter down to the exact bill of a product you want. This really helps with product development, sort of keeping configuration management of the different components. How does this interface with that? Oh, I forgot to check it with product 7. Well, if everything's in an overloaded BOM and you've got some tools to help you, that's a great way of managing it. So that's why people do it that way a lot these days. The challenge is that then when you think about sharing that with other systems, well, if people are not familiar with that concept or don't recognize how that system is managing it, then they may understand the bill of material that they're sharing across the other system. They may look at that and think, well, that's the complete bill for the product. Okay. Well, it is, but it's the complete bill for the product and all of its brother and sister products. So it's a little more than you really want. So when you go to put it from the PLM system into the ERP system, let's just use that as a simple example. If you put it in there and you think, well, that's the bill for product 1, it's really the bill for product 1 plus a bunch of extra parts. So if you didn't understand that, so this is where the person comes in the integration process, if all you understood about a bill of material is it is a parent and some children, then you could get this integration to behave properly. You'd get all the children over, you'd get the parent over, you'd create the links back to the parent, right? There's some complexity there, but if you've got that down, you'd figure that out. That's fine. But then 2 months later, when somebody in the ERP goes to order this product and they say, yeah, we're going to build 1,000 of those. If they work on this overloaded BOM, guess what? All the parts that were for product 2, 3, 4, 5, 6, 7, 8, all those, they ordered 1,000. Yeah, or 10,000 or 100,000 extra of those parts because the bill wasn't right, because the interpretation, the understanding of the nature of that bill was wrong, right? So just bad concept, little detail, 100,000 extra parts. Whoops.
Well, and it's funny because listening to you, I'm thinking, lots of times I put it into things that are not digital related. So I'm thinking about grocery list. Okay, I'm going to make 3 different kinds of cookies. I have they all have the same basic ingredients: egg, sugar, what you like. But I'm going to put chocolate chips in one. I'm going to put peanut butter and so. If I came home and my husband's like, okay, let's make cookies, and puts all of it in one bowl.
Bingo.
That's not going to be good, honey. That's just not going to be good.
No, thank you for my chocolate chip, raisin, walnut, cranberry cookie.
Right. Although somebody probably sells one of those.
That's true.
But you're right. And so then you've got too much of one thing, but probably also not enough, right? Because it's overloaded. So you've got all of the standard pieces plus the variable ones.
Right.
You've got you wouldn't multiple be able of the variables.
For example, you wouldn't be able to, like you said, if you took the overloaded BOM and you were trying to make a bunch of product 1, what you've got left over is not enough to make product 2.
Right.
Because the pieces that were in common, you only got enough of those for product 1. So anyway, it would really relate to or yield a big mess.
So understanding all of that, and I think we used the word character of the data earlier in the conversation. How does that impact what you actually do with the data?
Yeah. Well, I think there are a bunch of things that you want to think about when you're thinking about the character of the data that are going to dictate what you do with it, what you can do with it, what you should do with it, that sort of thing. I guess terms are good here. Terms are important because we can really get confused if we don't have a good language to talk about this. And it's funny. I think there's some good, easy language that we can relate to, kind of like the recipe example. And then there's a little more academic language. So let's touch on both.
Yes, please start. Are you going to start with mine and then get to yours?
Yes.
Okay, perfect.
Well, I don't call it mine. It's going to make me sound fancy, and I'm not fancy. But I think that the more accessible language is talking about traits and behaviors. And this comes back to something you mentioned in the introduction about static and dynamic, right? Because you have to think about the complexity of the dynamic nature of things when you're thinking about these systems and integration. Well, when you think about the data, you also have to think about the data as it exists when it's just at rest. But you have to think about how this data behaves naturally, because a lot of this product data has behaviors to it. It's time-based also. Or can be. So you have to think about traits, things that are just observable. When I look at this data, it has this trait. It looks this way. It is this size. That kind of thing. But you also have to think about behaviors, right? So what does it do? I'll give an example of one. A simple behavior is it gets revised and it gets matured, right? And those maybe are two different things. Revised may be just different versions over time. Matured may imply, for some people, it gets revised over time, but different revisions, different iterations of that have different meanings behind them. Like, well, these are work in process iterations, but that one, that's a released iteration.
Okay.
Right? And so you'd use those differently, because a released one you can use in manufacturing the product, but the work in process ones are just there maybe for history. Anyway, you get the point that time-based thing, that behavior is important maybe to understand that maturity process. I don't know even how you put those together. Life cycle, I guess, is the best word for it.
Right.
That matters in understanding the nature of that data, because some data doesn't do that, or it doesn't mature that way. And you need to know that when you're working with it. So I think those are two words that are important: traits and behaviors.
Okay.
Let's get a little deeper. There's another word, and these I think of as sort of more academic words. They're good. They're good language, though. The first one that you hear a lot in this discussion is taxonomy. And taxonomy, the way I think of it, and for those out there who really are academics, and when I get this wrong, I apologize now, but I think of taxonomy as it's a classification system, a way to categorize things. So that's important when you're talking about the data, right? And those traits I mentioned a minute ago, you want to put things into certain buckets, categories, whatever you will. And that taxonomy is very helpful to understand, in my product data, I have specifications. A subgroup of specifications might be models, right? Because there are models that can define the specification of a product. Like that's kind of a grouping. But then a totally different kind of product data is maybe a process, a workflow process, or a manufacturing process. That's a different animal. A bill of material. So there are lots of different things you might put in a taxonomy to understand the kind of data you're working with. That's good. That has a shortcoming also, though. Taxonomies aren't particularly good at representing that behavior piece I mentioned a minute ago. And I think there's another term. So, all right, we're going further down the academic term rat hole.
The fancy words.
The fancy words. I think this is a good one, though. Ontology, right? So an ontology goes beyond a taxonomy. It does some of those same things. You categorize things and you put them into buckets. But an ontology also describes relationships, how things relate together and work together. And that starts to get at the behavior piece. That really helps us understand, like an ontology could represent that bill of material we talked about a moment ago, right?
Right.
So if you've got a parent and a child, then you may understand that kind of relationship. There's a hierarchy, or parent-child relationship, or generational, or whatever you want to call it, between those components. And in an ontology, you would understand that. You would define that, hey, there's this thing called a bill of material component, or part, or item, or whatever language you want to use for it. But it also has a relationship back to itself right? Back to its own type that could indicate that parent-child. And an ontology might go further and explain things like, well, it can also have a relationship known as an alternate or substitute or repair part, but there are all these meanings, and an ontology lets you capture that.
Gotcha. All right, that makes a lot of sense. I mean, and I can certainly see as we're getting a little bit deeper how complex this question becomes about the character of the data.
That's right.
So one other term that I've heard is, and this is very much in 3D data translation, and particularly in GD&T, is semantic or PMI, like for semantic PMI versus graphical PMI. So what is, I mean, I can explain that in terms of PMI, but why don't you do it for us in terms of data in general?
Your example is a great one, though, and I'll try and give another one because for me, again, not being an academic, I need examples to make sense of a lot of these myself.
We're engineers.
That's right. But I think semantic is when you're able to describe something about it, like behavior, that a machine can understand, that a machine can do something with, right? Not just what humans, where we already understand the concept and apply the concept to the data, and then we get that together to get meaning. But semantic data has the meaning sort of embedded with it so that, anybody can understand it without having a context. And again, academics, please don't come for me if I got that wrong. That's how I know it. But so an example like you just gave of PMI, product manufacturing information on a CAD model, if it's graphical PMI, something like hole depth, right? You call out a hole on a model and you say, oh, it's 1 inch deep and a 1/2 inch bore. Okay, so there's 2 values there and they each mean something. But in graphical PMI, those are just lines that are stored, right? And you have to interpret them against a standard of GD&T to know how those lines come to some meaning. Whereas semantic PMI, that symbol is actually...
it's a whole symbol.
Exactly. It's carrying information with it that says, this means a hole, and this value means the diameter, which is this, right? Because a hole looks like a cylinder, and it means this thing. And then the depth is this. And so it's calling all of that out in the data set itself. Now, how it does that, I don't know. That's magic to me. But
we can talk about that another time. I can tell you about it.
Excellent. But the other example I would give, coming back to our bill of material we were talking about a moment ago, is lots of people will represent a bill of material as a table, as a tabular thing.
Right.
And they'll put the parent up at the top and they'll put the children underneath it. Okay, that's kind of logical. Parents at the top, everything's below. Okay. And they'll also put in they'll also put in a column that is, they'll label it, level or hierarchy, or they give it a lot of different names. And they'll put a 0 or a 1 in there, right? And the 0 means you're at the 0 level, and the 1 means you're indented 1 level below, and then a 2 and a 3. So you could have a multi-level bill of material. And there's some assumptions in that if you know how to rework those or interpret those assumptions and what to imply, you can get a true multi-level hierarchy out of it. But the fact of the matter is, it's just integers in a table. It's not semantic. It's not. Right. It's not explained.
The magic is in your interpretation, your understanding of those.
Correct. Right. So that's one of those places where a semantically rich bill of material would look a lot different. You would need to make connections or relationships between the parent and the children and say, look, this parent uses 2 of this child, and there would be a relationship and there'd be a quantity on that relationship, and there would be things in the data set that explained the number 2 on that link means quantity.
Which requires a whole lot more, I don't want to say thought, but basically structure, et cetera, basically more understanding. It's more complex to create that. But then once you've got that created, it's so much richer.
That's right.
Of data, that you can do so much more with it.
But it's going to let you move that data around, maybe across different models of the data, right? The different data models we talked about earlier, because the machine can then interpret it and do some of that translation between the systems. And so, if you've got a semantically rich data set in system A and same thing in system B, or they understand how to read or create semantics, boy, that integration can get a lot easier in the middle. And not to get off topic, but, and this is where AI comes in, right?
Of course. Machine readable.
Yep. AI might even help us with some of this when our semantics aren't quite right, or they don't fully understand each other. So there's a lot that's coming in technology that could help us with this problem. But until it does, we have to understand the character of this data instead of just, relying on machines to do it for us. So all the having ontologies and semantics in our data and that kind of thing is great, but yeah,
you really need to right. And you really, all of the terms we just discussed, the main point we're getting at is that you really need to understand the character of your data in order to develop and apply ontologies, whether you call it that or not. Call it behaviors, call it ontologies, but if you're fancy or if you're not fancy.
Right.
But the thing is, it's using your understanding to actually reuse and connect the data in useful ways.
That's right. And I think tying it back to those academic terms, like you said, and what people are doing today is, if you're building out a digital thread, you're working with existing systems that you have. Maybe you're putting in a new system, right? So you're evolving what you have. And the idea of having an ontology to help you do that is great. That sounds fantastic. But, for those of you that have nothing to do after listening to the podcast, go out and Google, ontologies and product data ontologies, and you'll find some really good academic stuff. If that's your bag, fantastic. Actually, call us if that's your bag. But it's kind of esoteric, and it may not apply to your situation. So if you're really trying to get something accomplished, you may not be able to get all these great things going. And what you really need to do is understand the nature of your data, the character of it, and how you are going to connect it in the pieces of the digital thread that you need. And I think maybe the easiest way to talk about this is I've got some examples if we've got time to go into that.
I was going to say, because you know what? I went into engineering because I couldn't, math by itself was too abstract, too theoretical. Went into engineering because I could apply that math into something that I could actually see. So help me out with that. Give me some examples. Make it real. Put it on the board, Professor. I want to see it.
So let's start with the document. That's an easy place to start in product data. We got lots and lots of documents, whether they're paper or digital, or they've been decimated into records that make up a document. Okay, whatever. Let's call it a document. And I'll start with the most common representation I see today, which is a digital document that's represented by a file, like in Word. So we won't even get to CAD yet, so leave CAD out of it.
How can we use Excel? Because, it is the Swiss Army knife of
That's
all
fair.
systems.
That's fair. And boy, does it get used that way. Anyway, I digress. So we got a document. And a lot of times in the concept we're talking about here, it's going to be a product specification. It's going to tell us something about the product. Paint, material, finish, any number of things. But you got this file and you need to get it from system A to system B. This seems really simple, right? It's pretty trivial. We do it all the time on our computer. I drag it, I drop it, it's easy. Well, when we want the systems to do it on the back end, also not that hard to copy a file around. What gets tricky is, did you get the right file, and making sure you kind of maintain the integrity of its relationships and where it fits and how it's applied, its configuration, right? Or the configuration of your product as it relates to this one spec. So what's tricky about it? Well, a couple things. Let's come back to our terms, the traits and the behaviors of a document. So traits of the document. It has metadata. This is not a shock to anyone, right? But it has information about what's in that file, like a doc ID, some kind of identifier that says, hey, uniquely, it's 1, 2, 3, 4, 5, 6, 7. That's its part, or its identifying number. It has probably a title. What is it? Material spec 6061, T6 aluminum, whatever. Not that you'd need a spec for that, but anyway, it has maybe an author who wrote it. It could have other things, a date, a thing, other information.
Revision history. It's, and it's funny because you say, of course everybody knows this. I don't know. Like, I mean, if you're using the example of Word, I don't often go in and look at the properties and like all of those things. So, it's pretty easy not to know those things.
That's fair. And sometimes people don't fill them in, right? So, I mean, you're right. I assume it a little bit because we're, on this podcast talking about this stuff and all PLM. But you're right. Not everybody knows that kind of information can travel around with files and that it's there. But it is. Those are traits that I guess it can have. Not everybody fills it in, but it's there.
Right.
Another thing that's important, because you mentioned revision history a second ago, I'm going to put that into the category of behavior and come back to that concept I mentioned earlier, right? When I said revisions or iterations and possibly maturity. So a spec, right? And this is not just any old document, but a specification for a product is likely going to have a revision history and some maturity, and maybe they're kind of intertwined, right?
Right.
You might identify those iterations with numbers, with letters. Maybe you're not identifying them because, Office is just taking care of it for you in the background with SharePoint or something. But the point is they're there and there's some meaning behind them, particularly with that maturity piece, which is, well, there's a bunch of them that are you were just changing the file. And there's a couple of them that are, it's ready. I got it reviewed. It's been published. We agreed. That's the thing we're using to define the product. And then we made some enhancement to this material and made some more edits. And there's a bunch more versions that don't really matter to me. But there's another version that is the released one that's like, that's the one I want to use today. Okay, so we've got this behavior that's sort of a time marches forward and a couple of points in time that you want to pay attention to. That's the way specifications behave generally, right? And, hopefully lots of listeners are out there going, yeah, you're right. I get it. Product specs. So those traits are pretty common, no matter my PDM system, whether I have one or not, that kind of thing. And this behavior is pretty common.
Well, but you said that's the easy example.
It is. But let me tell you a story about it before we move on to the next example.
Okay.
Right? Because I want to apply why it matters. Let's say you're moving that file across. It's relatively easy, particularly if you know a friendly IT guy that you're like, hey, can you hook these up? And I want to get it from this system to that system. Sure, I can do that. But if you don't explain some of this about the revision history and the fact that actually I'm going to have 20 copies of that file, maybe you keep them in different folders. Maybe it's a PDM system handles it for you, whatever it is. They all have the same file name, but their metadata might indicate something to you about that behavior, like maybe you track that revision number. Maybe that revision number is embedded in it is a clue about the maturity, like it's A.1, A.2, A.3. Those are all the intermediate versions, and A is the released one. Okay, if you don't understand that, right, and that's a combination of that behavior and those traits.
Right.
If you don't understand it, then your friendly IT guy who's going to help you out moving this stuff over may just grab A.1. Hey, that sounds good to me. It's the top letter, the top number. That's probably the one you want. Reality is no, it's A you wanted because that's the released one. If you didn't understand the character of the data and how to interpret it, you could get the wrong one. You move it over to the other system. Now this digital thread that you're building out, it's not really as good as you thought it was because you got the wrong version of the spec that you wanted. It starts to fall apart. So anyway, I just wanted to touch on why that matters.
No, and I can totally get that. I mean, it's going back to semantic versus graphical PMI. Like, if you interpret that graphical PMI incorrectly, then everything breaks down after that.
Yeah.
All right. So again, that was the easy one.
That was the easy one.
Still has a problem. I mean, it still is very easy. It sounds like it's very easy to make a mistake with it. Right. So I can't imagine if you get more complex, how much easier it is to make mistakes with data.
Let's come back to the bill of material, right? We mentioned one way earlier about an overloaded BOM. Okay, so I'll give you one that's a little bit sneakier. First, let's come back to our traits and behaviors. So traits, what are the traits of a bill of material? Well, you've got components in there, and a component is really just typically a collection of lots of metadata about that component. A part number, a description, maybe a revision. So you could have that. What's that?
Relationships. I mean,
that's another one,
okay.
right? So relationships are another big trait of that bill of material because you can have them between the different components. Here's another fascinating part. Those relationships, back to ontology, can have meaning. So you might have a relationship that's the parent-child relationship. We all expect that with a bill of material. But you may have other kinds of relationships too. So let's focus in on a specific one a lot of people will track. Alternates and substitutes. So for lots of products, particularly ones where you're making a lot of them, for certain components, you need to define what is an acceptable alternate because you can't get the one that you need from your supply chain disruption or, in that part of the world, we buy this component. In this part of the world, we buy that component.
Use these materials versus those materials. Yeah, I can definitely see that.
Right. So that's a big part of engineering definition a lot of times is, make my design like you would make it here in our local country and then globalize it. Give me all the alternates I need for doing it in other parts of the world or, whatever it may be.
Give me my overloaded BOM.
So this, though, I won't call this an overloaded BOM. Technically, it sort of is because it's got more in there than you need, but it's defined a different way because it's not, these are all the parts you need to make all the things in the family. These are component by component, perhaps.
I see.
Hey, this part has these alternates or these substitutes.
Right.
Now,
so it's not a different product or version. It's just using a different component because it wasn't accessible, it's not permissible in that country, et cetera.
Right, exactly.
Gotcha.
And this is where it gets tricky because I'll tell you the first dirty little secret about this is that term alternate and substitute, there are definitions of each of those words that most companies do not agree on. It's like a 50-50 shot. So,
of course,
a lot of companies, an alternate means that you could swap this component out for that component anywhere that component's used. A substitute means you can swap this component for that component in this subassembly, but not in the other subassemblies. Well, that definition, some people flip-flop it 100%, right? Okay.
And we have another interoperability problem.
So there's a problem, but regardless of that, they represent it sometimes in interesting ways. A lot of people will put it in a bill of material as that part is in there at the right level, shown as a child, but it's listed as quantity 0. That a lot of times is sort of a substitute thing, right? Which means that you could swap it out. But anyway, the whole point of this, because I'm getting way too deep in this, is the representation.
It's clearly a subject that you're very passionate about.
It is, because it make a lot of messes. If you represent it not totally accurately, and it's hard to represent it completely accurately, or it has been hard with the technology we've had, then when you go to move it across or share it with another system, boy, interpreting that is tough, particularly if there wasn't enough data. Like you really got to apply some other context to understand, that component is an alternate for that one. It's not just that it's swappable in that subassembly, and you've got to know, well, there's only 2 microchips in that subassembly, and those must be interchangeable for each other. It's that kind of stuff. And if you don't understand the nature of that, the character of your data, right, then you're going to get it wrong. You're going to apply the wrong rules, wrong logic when you move it over. Or maybe you'll get it right 98% of the time. But to 2% that you didn't cover for in your logic, you get it wrong. And maybe you'll never know until
something happens.
Exactly. So
and
anyway,
the further down the chain that you are when that problem crops up, the more expensive it is to fix, correct,
even
recall, whatever.
Even find, right? That's the one that is really tough, is when people are like, something's wrong, but I have no idea how that data got there. Right? Like unwinding what you've done in a systems integration, particularly if it was multiple steps and there was some logic that somebody had to infer this and look at that. If you didn't know that was what was written because somebody misunderstood the nature of the data they were working with, even finding it's tough.
Yeah, I can imagine. It's all of that, I mean, it's, we've talked a lot about the quality of the data in past podcasts. But this brings really a whole another level of understanding, not just the quality of the data, but what that data is and how it behaves and the structure. And there's
the
a
quality
lot.
of how you handle it, right?
Yeah.
That's a big piece of it. And the quality of the data you get out the other side is related to the quality of how you handle it. It's sort of like, microchips in a clean room. If you don't have a clean room and you just pick them up, no gloves, guess what? The product is ruined on the other side because of how you handled it. And that's the same thing here.
That's a great analogy. I like that a lot. So it's, and because integration is essential to the digital thread and building digital twins, understanding how to move with that, understanding, like you said, the character of the data and how it behaves is really critical to building that out and being successful.
Yeah.
So, this has been a fascinating discussion now, but you did allude to bringing, with all of this integration, there's another piece to this, right? And at some point, we need to get Tim in here. We need to get.
I agree.
We need to get Tim Knows, our VP of products, in here to talk about what he's seen in the integration space. So
because not to dive into a new topic, but it's all the stuff we just talked about is right, and it's a big deal from a conceptual perspective, right? The logical perspective of handling the data. But there's this whole other realm of the technical aspects because it's digital data we're talking about. So I agree. We got to talk to Tim.
There's understanding, and then there's actually applying that understanding. Again, math and physics. So, all right. Excellent. I'm looking forward to it. So thank you for joining me today, Jonathan. This has been a great discussion.
Absolutely.
And to our listeners, if there's something we missed, a point, or if you have any questions, please reach out and let us know via social media. Subscribe to the podcast wherever you can find it. But if, or even if there's, you're like, okay, enough with the data already, I'd like to talk about something else. Reach out, let us know. This is part of a conversation. It's more interesting if you're in it. So please, we'd like to hear from you.
Even feel free to, give me better definitions for taxonomy and ontology and stuff like that.
Right. So, and everyone, until next time, stay sharp.
Thanks, everybody.
Thank you for being here and listening to this episode of Stay Sharp with Razorleaf. If you have any questions about data quality and AI, we'd love to have that conversation. So just leave a comment on our post or send an email to podcast@razorleaf.com. We appreciate all the feedback we get from our listeners, so please be sure to send us a note. And also, please subscribe to our podcast on your favorite podcast platform or our YouTube channel. Until next time, stay sharp.